Okay, class. Greetings from Kuwait City, Kuwait. Well, actually my office today. But when you watch this, I'll be far off in the Middle East. Today's learning objectives, last time you learned about diffusion. Diffusion was all about the flux, right? The flux is the amount of material that travels per area per time. And that can be discerned. We decided the last thing we did in class was something by something called Fick's first law. Fick's first law basically said that the flux of material, right? If we go back up to it, the amount of material is equal to the negative constant of proportionality that we call the diffusion coefficient multiplied by the gradient in the concentration. This is the spatial gradient. So literally, physically through the material, you're going to have a higher concentration over here, a lower concentration, and so it's going to move down the concentration gradient. Okay? So that's Fick's first law. So the first thing we'll talk about today, our learning objectives, is using Fick's first law to solve steady state mass transport problems. The next thing that we're going to cover today is using a generic solution, because there's more complicated ones out there. I'll explain later. But we're going to use a generic solution of Fick's second law, and that's for non-steady state diffusion. Okay? So we'll describe what's the difference between steady state and non-steady state as well. The last thing that we're going to do in today's video is identify what other conditions like temperature impurities, imperfections, all of these things, how will they influence diffusion rates. Okay? So let's start out with an example of Fick's first law. So let's consider a metal, right, a material like a metal, and it's separating two different gases, the same gas on either side, but with two different partial pressures. Or in other words, the gas on one side is much more concentrated than the gas on the other side. So this could be a tank, right, a hydrogen tank in your vehicle, right? We make these materials to keep the hydrogen in, but since there's less hydrogen in the air and there's more inside, there's a concentration gradient. That means that you will have hydrogen diffusion. This was one of the early problems with hydrogen vehicles, is they didn't know how to store the stuff because hydrogen is so small that it can leak through lots of vessels, even metals, right? So let's go ahead and get started on this one. We're going to start by drawing an axis to represent this, right? So let's draw a concentration profile. Here we've got the concentration at side B, so I'm going to draw the two sides of our material. This is where the material starts, and this is where the material ends, side B. So this would be the concentration of the gas at the outside, okay? This over here would be the concentration of the gas on the inner wall of the container. So if this is the pressure vessel, then this whole region in here in the middle, this would all be the material, like the metal, whereas this is gas and this is gas. Okay? Now we said that there's different partial pressures, so let's go ahead and label that. Let's pick a different color, and let's say that this is partial pressure on side A and this is the partial pressure on side B, and we're going to define that partial pressure on the side A is greater than the partial pressure on side B. This just means that A is inside the tank, so it's dense, and B is outside. Now, steady state diffusion. Steady state diffusion means that the rate, or the flux, right, the flux of material that's being transported is not changing as a function of time. So it's constant. It's already reached equilibrium. It doesn't mean that there's no diffusion. It just means that the diffusion rate isn't changing, right? And under those conditions, we have Fick's first law, which is this. It allows us to draw a linear profile in the concentration gradient, right? So this is, I should have drawn, that on the x-axis we're plotting distance, right? This is x. So this slope right here, that is dc dx. dc dx. And it's constant. It will only be constant under steady state conditions. We're going to show you in a minute what it looks like under non-steady state conditions, but it changes things a little bit, okay? So this is our problem. So under these conditions, now that we know the basic setup, we'd like to figure out, under different conditions like how thick it is, or the diffusion coefficient, how much flux are we actually seeing, okay? So we can actually calculate that. The first thing we should do is figure out the exact expression for dc dx. Since it's the slope, it's just going to be rise over run, right? So we're going to take delta C over delta x. We're going to do the concentration at point A minus the concentration at point B. We're going to divide that by the position at XA minus the position at XB. Okay, so that's our slope here. Okay, So that allows us to define the concentration gradient. Now that's set up a little bit backwards than you normally see these problems. It's normally like y2 minus y1, x2 minus x1. They set these ones up backwards on purpose. The reason why is they want to go from high concentration to low concentration. You can do it either way, but you're going to end up with a negative sign. And so keeping track of the negative sign, I think it's easier just to follow the convention in the book, which is Ca, the high concentration side, minus Cb, the low concentration side, divided by Xa minus Xb. Right? You could do it the other way, but you need to add a negative sign. Okay? All right, so let's do an example. Hydrogen gas is purified across palladium. Actually, when they produce hydrogen gas, it's oftentimes not pure. And if you want to get pure hydrogen, then you can choose a membrane that hydrogen will diffuse across, that other materials like other gases, oxygen, methane, whatever else, it won't diffuse across. Okay? And palladium turns out to be a pretty good one for that. Problem is that it's just crazy expensive. And so because it's expensive, you want it to be very, very thin. And you also want it thin because you want this gradient to be as large as possible, right? So if you make x smaller, then the gradient gets larger, which is a good thing. That's going to increase your driving force, right? So a thin palladium sheet. We've already said that this is steady state because it's not changing with time, right? And we've said that the slope ends up being linear under that condition. So here's a table of diffusion data, right? In tables like this is the sort of data that you need to use to figure out what D is in these problems, right? So if we go back to our Fick's first law, we said that the flux, that's going to be, again, mass or amount per unit area per time. That's equal to negative D, the diffusion coefficient, dc dx. We talked about diffusion coefficient, that it itself is a thermally activated process. And you can sort of get the parameters to calculate diffusion at any temperature from a table like this. For example, from this table, you've got this guy right here, d naught. That's the pre-exponential, if you recall. It's d equals d naught exponential of the negative activation energy over RT. RT, if you're doing this per mole of substance being transported, or it can be over kBT, Boltzmann constant, if it's per atom. And so we need D naught, that's this one here. But you also need QD, that's the activation energy for diffusion. And here they're showing it in both values. You've got kilojoules per mole, or you can do EVs per atom. Okay? So from these two values, we can calculate the diffusion coefficient for any temperature we like, right? Which is pretty great. Now sometimes the material will change phase. We know that iron does, right? This is, the host metal is alpha iron, but alpha iron turns into gamma iron, austenite. So ferrite turns into austenite, right? And it even turns into another phase higher up, right? So when you calculate diffusion, there's typically temperature ranges where you're allowed to use it, which correspond to where the phase diagram says these phases exist. So that's the host material. These are these two constants. The last thing we need to know is, well, what's the diffusing species, right? Because if the host material is iron, are we talking about iron diffusing in that host material? That's called self-diffusion, you remember from last class. But it might be something else. What if it's carbon, right? This is really important. Carburization of steel is a big deal. They'll put carbon on the surface and let it sort of diffuse its way into the material, right? So the diffusing species will also matter. And just look at the impact that some of these things have, right? Let's start out with just self-diffusion. Iron diffusing an iron metal. At 500 C, it's got some value to the negative 21, right? You heat that material up, exact same phase, exact same diffusing species, and it goes up, when you're at 900 C, it goes up to something 10 to the negative 15. So that's 6 orders of magnitude difference. That means that diffusion, when you go from 500 to 900, is 1,000,000 times faster for this hosted metal, right? For this diffusing species and the host metal. Pretty remarkable, but that's the general trend because it is this exponential. Heating it up really gives you massive benefits. That's why heating is such an important process in a lot of material science, okay? Then take this one, right? Carbon diffusing in alpha iron, right? So carbon diffusing in alpha iron, 10 to the minus 12 at 500 C. Compare that to this one. Iron diffusing in iron, right? That was 10 to the minus 21. That's 9 orders of magnitude. That means that carbon at 500 degrees Celsius diffuses 1,000,000,000 times faster than iron, right? So carbon's way, way faster than iron. And hydrogen, it's going to be extremely fast too. Carbon's a nice small atom. Hydrogen's even smaller. So it would make sense that it would actually diffuse much faster than even carbon. I'm pretty sure it does, okay? Okay, so that's where the D is going to come from. We know how to calculate delta C, delta X, so now we can go ahead and solve one of these. So let's work a problem. Okay, here's the example question. It says you're working for a company called Intech, and your job is to harden titanium by the diffusion of carbon. Right? Regular pure titanium is not very hard, but if you add carbon to it, it gets harder. So first off, think to yourself, why do you think adding carbon makes it harder? Okay, we talked a little bit about hard materials, and those are things that don't allow dislocations to move. So first off, why would a titanium carbide be harder than a titanium? Well, for one thing, titanium carbide is going to start to form covalent bonds, right? They're going to be bonded, right? Now you've got an anion and a cation, and so anytime you have an anion and a cation, if we go back to our chapter 8, where we learned about the deformation mechanisms in ceramics, you remember that you had to have the positives slide past the positives, the negatives slide past the negative. That cost a lot of energy, and so these things just don't slip very well. So for one thing, it's probably going to be harder because there's no slip systems that are acceptable. They're too high energy. But for another reason, the carbon might also be sitting in interstitial sites, right? And if it's doing that, then if it sits in an interstitial site, that also impedes slip from occurring. So in any case, we have pretty good reason to believe that titanium carbide will be harder than titanium, so we want to add it. And this problem is about how to do so. It says the concentration of carbon at 1 millimeter into the surface of the titanium slab is given, right? 0.68 kilograms of carbon per meter cubed in the material. Kind of a funny way to represent concentration, but it works, right? It's an amount per volume. That's a concentration. Then it says at 3 millimeters, the concentration is 0.25 kilograms per meter cubed, okay? That makes sense. The deeper into the material you go, you should have a lower concentration since you're starting from the surface, okay? The temperature of the carburizing environment is given, 925 Celsius, and it says, and the rate at which carbon is entering into this 2 millimeter thick region is 1.27 e to the negative 9 kilograms per meter squared per second, right? So they're giving us a flux there, right? That is an amount per area per time. So they gave us a flux that's entering this 2 millimeter thick region. Let's go ahead and draw this before we get too confused, right? So when we go from 1 millimeter up to 3 millimeters on the x-axis, right? Within this region, we know what the concentrations are. We know that up here, it's at 0.68, the units of this one, again, were kilograms per meter cubed. But down here at the side at 3 millimeters, it was only, 0.25 kilograms per meter cubed, okay? And what it just told us in the question is that the flux traveling through this region, J, is equal to 1.27 times 10 to the negative 9 kilograms per meter squared per second, okay? So we know what the flux is. We know our thickness. We've got our concentration gradient. I'm just going to go ahead and remind us that that would be a linear concentration profile in the amount of carbon in the titanium because we're assuming this is steady state diffusion, right? It then says, let's see, where are we? What is the diffusion coefficient for this particular treatment? Okay, so they want us to figure out what is the diffusion coefficient. They're not going to give it to us. So easy enough, we're going to use Fick's first law, and we will say that J, our flux, is equal to the minus of the concentration, minus of the diffusion coefficient multiplied by the gradient concentration, dc dx. Okay. So for this, we can go ahead and set this problem up. Let's say that we know the flux. We're going to solve for d. So d is going to be equal to J divided by dc, dc dx. And then we have to remember the negative sign, so that'll be negative up here. That's a funny J. Okay, so let's go ahead and plug things in. We'll say that J is known. That's 1.27 e to the negative 9 kilograms per meter squared per second. It's smart to keep your units here, right? Because if units don't match up, you're going to need to fix them. And keeping your units is the absolute best thing to do on all these problems. Just get into the habit of it. This is divided by the difference in the concentration, right? So as we go from here to here, remember we're going to write it A to B, right? High concentration minus low. Okay, so that's going to be 0.68 minus 0.25. 0.68 minus 0.25, don't forget our units, that's kilograms per meter cubed. Divide this whole thing by the distance in x, that's going from 1 to 3, those are in millimeters. But up here, the units, we know that since this is meters squared and we're dividing by meters cubed, in order for this thing to come out with the right units, we should put our x in meters as well. So this is going to be 0.001 meters minus 0.003 meters. Okay? And we'll see that some things are going to start canceling out. For one thing, if we just do a unit analysis, I'm going to change colors for the unit analysis here. Oops, I think I got that. We're going to end up with, so the top has kilograms, and the bottom has kilograms, so those would cancel. This had meters cubed divided by meters, so this ended up being meters to the fourth, whereas this one was meters squared per second. So the kilograms are going to cancel. 2 of those will cancel with those, and we're going to end up with 1 over meters squared per second. Just a good double check to make sure that you're doing your algebra correctly. If we go back up here, what should be the... Oh, I messed that up. Sorry. 1 over s divided by 1 over meters squared. I messed that up. Excuse me. That should be meters squared per second, which is the correct units, which we double checked from our table. They should be in meters squared per second. So double check your algebra. It'll be helpful. All right, now we know we can go ahead and plug those in, and we're going to get an answer in meters squared per second. So I'm going to plug them in. Okay, and I get for an answer 5.9 times 10 to the negative 12 meters squared per second for D. So D, our diffusion coefficient, I get 5.9 times 10 to the negative 12 meters squared per second. Okay, let me pause for a second. Okay. Having worked through an example of Fick's first law, let's keep moving on. Now we're going to talk about Fick's second law. And Fick's second law applies under non-steady state diffusion. Non-steady state diffusion means that the diffusion profile is changing with respect to time. For example, here's a plot of concentration in a material as a function of depth in the material, and then these different lines that you see sort of going this way, that's as T approaches infinity, right? If you hold it for a longer and longer time, these concentration profiles slowly change, and you notice what they're trending towards, they're starting to look linear. So if you take a non-steady state condition and you let it equilibrate, right, give it long enough time, whatever time scale that matters for your material, it will eventually reach this nice linear profile, okay? That's steady state condition, okay? Or sorry, non-steady state turning into steady state. Okay, and we can see some cool examples of this. We're going to watch this YouTube video. So check this out. In this example, they're going to start out with different pennies. All right, Canadian pennies.
First, get 30 grams of zinc sulfate. Then add 100 milliliters of water and...
Okay, so he's starting out with zinc sulfate. Okay. Their pennies are pretty much like ours. They're copper, right? The inside's probably a little bit different, probably zinc as well, right? But they're starting out with pennies that are on the surface copper. They heat it up. Why do you think they're heating it up? So zinc metal's going in there. Okay, so they're heating it up, right? Because they want that zinc sulfate to dissolve and become completely ions in solution, because we're going to use those ions to plate them onto the penny. So we need them to get dissolved first, and heating speeds up that process.
Now get a copper penny, or any piece of clean copper for that matter, and drop it in. It has to touch the zinc metal for the reaction to occur.
Okay, it's got to be touching, right? Because you need electronic, right? This is an electrochemical reaction. There has to be the exchange of electrons. So if it's not touching those, then you won't get the reaction to occur.
What's happening is the zinc is reacting with the copper and dissolving, while delivering electrons into the copper. The copper, now charged with electrons, will reduce freeze surface, giving a silvery color. This takes about 10 minutes, so I'll skip over that. Here you can clearly see the more silvery color of the penny.
Okay, so what is that silvery color, right? We had copper touching zinc, right? We had zinc ions in solution. If you look up the standard reduction potentials, you would see that one of these is more favorably oxidized than the other. In fact, the one that's being oxidized is the zinc, right? So you're losing zinc, it's dissolving, and you've got these zinc ions in solution already, and they're going to be reduced onto the copper metal, right? So they're plating onto it, which makes it look shiny.
Just turn a copper penny into a silver one. Sure, it's a trick, but it looks cool. Now for the most amazing trick, turning it into gold. You wash it first. Simply put the coin directly onto the hot plate, heated to about 300 degrees Celsius.
Okay, what's going to happen? You've got copper and a thin coating of zinc, excuse me. When you put that on a hot plate, what do you think will happen? Well, first off, the heat is giving us the ability to diffuse quickly, and then it's going to move down the concentration gradient. So if you have a large concentration of zinc at the surface, and you cool this thing, and you heat it up and give it time and temperature, that zinc is going to want to become more homogeneous to the copper. So watch what happens.
As it heats up, the zinc diffuses into the copper and produces a yellow brass. At first it's going to look coppery, but that's because it's still hot. After you cool it directly with water, it will now appear gold.
So we know that this brass color, that's just a mixture of copper and zinc.
The brass layer will eventually wear off. Anyway, that's the trick of turning copper into silver and then into gold.
If you were to leave that on the furnace for a while, on the hot plate, what do you think would happen, right? The amount of copper versus the amount of zinc, there's much, much more copper, so that zinc's going to keep on diffusing in. And if you do it too long, that surface won't look nice and gold, right? Because it's going to approach the steady state condition where it's even throughout or close to even throughout. And so your surface concentration is going to go down because you're not keeping the surface concentration pinned at some value. And so because of non-steady state conditions, it's not going to maintain that yellow color, right? All right, so non-steady state conditions, since it's changing with respect to time, we need to have an expression that has time in it. If you go back up here before, because it was steady state, our Fick's first law, where'd it go? Right here. Time's not in here, right? We're assuming that things are constant with respect to time. So now we need one that includes time. So it goes as follows. The concentration with respect to time, so the change in the concentration with respect to time is going to equal the diffusion coefficient, this time it's a positive, not a negative diffusion coefficient, multiplied by the second derivative of concentration with respect to x. So this is the gradient, the derivative of the gradient, right? The second derivative, or the derivative of the gradient of the concentration profile, right? This is a classic partial derivative equation. When you guys have taken PDEs or engineering calculus, you'll learn how to solve some of these by applying boundary conditions. Now in this class, I'm not going to assume that people already know how to do that. Instead, I'm just going to show you what one typical solution looks like, but we won't solve this ourselves. We're just going to use the solution, okay? So, for example, one of the really classic examples of this is called the semi-infinite solid with constant surface concentration. So let's change the color on that so that you know that this solution only works under these conditions. The semi-infinite solid means the following conditions, right? First off, before diffusion, any diffusing atoms are uniformly distributed with some initial concentration. So in the penny, if that thing is solid copper, if it's a solid copper penny, then there was no zinc to start with maybe, right? Or if there was like 5% zinc to start with, then that's uniform all the way throughout, and we would take note what that concentration is, okay? The next assumption is that at x equals 0, that's going to be the surface, we're defining that as the surface, and then as you move into the material, we're calling that positive x values, okay? T equals 0 just before the diffusion begins. So we're going to start the stopwatch on this thing right as diffusion begins. And then these are our boundary conditions. At t equals 0, so right as diffusion begins, concentration equals the initial concentration all the way through the material. So from x equals 0 all the way to as deep into the material as we go. And this technically only works for semi-infinite solids. That means that it's a big solid, right? The diffusion distance goes way, 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 way in. That's important. Really, really thin things, it's going to change the solution. So this solution only works for semi-infinite solids. Things where the diffusion distance, which I'll talk about in a minute, is small compared to the width of the sample. Okay. The other boundary condition is that for temperature greater than 0, so for all times that we're considering, the concentration equals a surface concentration at x equals 0. So at x equals 0 is the surface. We're saying that there is a concentration which is not changing at the surface. That's important. The constant surface concentration gives us a different profile than if you put a finite amount at the surface and then let it diffuse, right? So these are really important differences. In the semiconductor industry, we're going to do a problem in a minute on it. They'll sometimes put a finite amount of, say, phosphorus atoms on silicon, and then they'll let that diffuse in. But they're not adding more phosphorus and keeping it fixed at the surface. They're letting it diffuse in, so that surface concentration would go down in that case. For this solution that we're showing you today, that can't be the case. The surface has to stay. So it basically means that you're constantly supplying new material to the surface to keep that concentration at CS. And then we also know that far, far, far away from the surface at x equals infinity, deep within the material, the concentration is still C0. So again, if this was a thin material, this would be violated. Eventually, we'd start building up the concentration in the material, and so it's got to be far away from it that it stays at the initial concentration. So if you meet these conditions, which is the only ones that we're going to do in this class, then we have a solution, right? You can solve it for other solutions, and you'll do so in PDEs, but in this class, this is the one we're going to use, and it's as follows. The concentration of your dopant at any position x, Cx, that minus C0 divided by the concentration at the surface minus C0 will be equal to 1 minus the error function of x over 2 root dt. So there's a lot there. Let's unpack it. First off, error function. If you haven't used error function before, it is what's called the Gaussian error function. You can read about it here. It's pretty interesting, actually. The error function is just something, it's a mathematical expression that looks a little bit like diffusion profiles. For example, this is the error function of x, and if we go from x equals 0 out to infinity, it does this sort of bended rise like that. And if we go back to our diffusion profiles, it kind of looks like it. That's why they use it as a potential solution. There's other solutions for these things that don't use the error function, that use expressions like a Gaussian. But for this one, it's the error function that we're going to use. If you've never used one before, we'll show you how in a minute. You've got x, the position at any position from the surface into your material. D, that's the diffusion coefficient from before, and there's time. So now, as a function of x and time, you can calculate the concentration, right? At any position you want, you can calculate the concentration at any time you want, right? So this is a really powerful solution, being able to use this one to calculate the changing concentration profile during non-steady state diffusion. Okay, how do you use the error function? Error function works like this. Everything inside the error function, this stuff right here, we will call z. Everything inside is called z, right? Error function of z. So if you know what z is, then you can use a table and you can look up what the error function of z would be, right? Or you could read it from a plot like this, right? You could say like, oh, well, they're calling it x, but we called it z, right? If z is 1, then you could say that my error function is something like 0.8 or 0.9, right? So over here, if z is 1, 0.84, right? So these tables are pretty handy. Some of your calculators can do them. Wolfram Alpha can do it. If we pull up Wolfram Alpha, it can do error functions. Google probably can too. I don't know if I've tried it. While that's pulling up, we will use tables in this class. If you have a calculator that can do it, great for you, but I'm going to teach you how to use it from the tables to get exact values. So let's say we want to figure out the error function of, 0.75, okay? Yeah, the error function of that is 0.7111. Let's make sure that's right. 0.75, yep, 0.7111. So you can look these things up in this class. One of the problems is in this class, if you don't have Wolfram Alpha or a calculator and you need to look something up, what happens if it's not shown on this table? Like let's say that you're doing an a problem and you need to figure out the error function of something like 0.52, right? What if z, the value inside of our error function, equals 0.52, right? You look at the table and you say, oh, we've got 0.5 and we've got 0.55, but I don't have 0.52. So what do we do? So you've probably seen this before in other classes, but we're going to do what's called a linear interpolation. A linear interpolation basically says the following, right? We know that our error function looks something like this. If this is z, and this is error function of z, right? It's doing something kind of like this. So we have data points every 0.5. And if you look at those and your points are zoomed in enough, it's basically linear lines between them, right? Now, if your points are too separate, like if they're really far apart, then it's not linear, it's bending and stuff. But if those points are small enough, like they are in this table, then you can just assume it's a straight line between those points without losing much information. It's an approximation, to be sure, but it's a pretty good one, okay? So the expression for a linear interpolation is as follows. Let's say that this is one of the points that you know. This is one of the points you know. We're going to assume it's a straight line, even though the real one might be doing something like this, right? Even though it might be doing that, we're going to assume it's basically a straight line between those points. So if this is x0 and y0, and this is x1 and y1, right? Or in our case, this would be something like 0.5 for z, and y would be 0.5205. I'm just reading from the table here. And then above that, we've got 0.55, and we've got 0.5633. Then we can go ahead and do a linear interpolation between these 2 points. And at any point along here, like anywhere, here or wherever else, we can figure out what those values would be. So we'll call the points where we want to figure it out, we'll call that just x and y. The expression for the linear interpolation is as follows, and you could do this yourself just by figuring out the slope and stuff, but if you want an easy formula, then it's right here. It's y minus y naught divided by x minus x naught equals y1 minus y naught divided by x1 minus x naught. Okay? So for us, we could go ahead and start plugging things in here. We could say, okay, we want to solve for y. We know what x is. It's x is, sorry, I switched names. I should have called it z, but x is z, is 0.52. We want to find out what the error function is there, okay? So let's go ahead and plug it in. We would say that y minus y naught, that's going to be the error function value below it, so 0.5205, 0.5205 divided by 0.52, that's our x value, right, our z value, minus the value below it, which is 0.5. Then this is going to be equal to the y1 value, that's this guy up here, 0.5633 minus 0.5205. And that will all be divided by x1 minus x0. So 0.55 down to 0.5, 0.55 minus 0.5. We can go ahead and solve for y by doing cross multiplication, and we find that y is equal to the error function of 0.52 is equal to, I get a value of 0.5376. 0.5376. Let's see how that compares to the actual value. It's going to be pretty close, but not exactly right. So if we go to Wolfram Alpha, let's punch in 52. Yeah, 0.5378, and we got 0.5376. So this is a great tool. Obviously, during parts of the plot where it's more linear, it's going to be a more accurate thing. So if you're doing the linear interpolation down here, it's mostly linear. You're going to get good values. Right here, it's going to get good values. But if you do it right at the bends, that's where you're going to have a little bit more error, right at the bends, but it's still a great technique, okay? So that's the error function, how you use the error function. So we've introduced a solution of the many, many, many that exist, right? One example of a solution of Fick's second law, which is just telling us what the concentration at any point is doing at any point in time, okay? At any position, at any time, it tells us what the concentration is anywhere in the material. Pretty awesome, okay? So you can see an example of how to do this. Oh, sorry. That's of the diffusion distance. Let's talk about diffusion distance for a minute. I'm going to put a great big, like, warning sign around this because people use it incorrectly. So I'm a little bit careful when I teach it. The diffusion distance is just a general diffusion distance. It's like an average. It's a ballpark. When you heat something up and you know what the species is that's diffusing, what it's diffusing into, then you could get an approximate diffusion distance under the conditions if you know them, right? Here's what the approximate diffusion distance is. It's equal to the square root of the diffusion coefficient times time, okay? Now, if you look at that, what we've really done is we've said x is equal to root dt. If we go back up here, if you plug in root dt, right, for x, then your error function just becomes error function of the root dt's cancel. It's just 1 over 2. So the error function of 1/2. What we're really saying is, what's the concentration? Sorry, that's when it's halfway through. So the diffusion distance is basically, we're saying when it's halfway between, 0 and 1, when it's right there. That's your diffusion distance. Okay? When it reaches about halfway point between where it started, which was 0, and where it's going, which is 1, it's approximately 0.5. So that's all that is. Or in other words, if we go back up to our drawings, right? When I say what's the diffusion distance, some of your atoms will be diffused all the way out to, what is this, 3 centimeters. A much higher concentration will be present at 1 centimeter, right? The highest will be at the surface. The diffusion distance is just saying what's the average point. That's all that's saying. It's like that point. That would be x in your diffusion distance, approximately. So don't use this incorrectly. All it is just a ballpark. If you want to know roughly how far atoms are diffusing, then this is what you use, okay? And you just plug in the diffusion coefficient, which you can solve for any temperature and time. And since diffusion has the units of meters squared per second, that's going to be multiplied by seconds, so your seconds cancel out, then you take the square root of meter squared, it's going to be a distance, right? Just going to give you meters, okay? And we've got an example of using that on YouTube if you want. Now let's do an example of actually using Fick's second law for a question. This has to do with the concept we described earlier. In the semiconductor industry, you've got pure silicon maybe, but we dope it for reasons that we'll talk about in a few chapters, in chapter 12, to change its electrical properties. So let's say you're doping boron into silicon. So it says boron is pre-deposited at 4.5 times 10 to the 20 atoms per centimeter cubed. So that's your concentration. Instead of giving you a mass, it's telling you how many atoms per volume. That's okay, we can work with that. It says on a silicon wafer with an initial concentration of 5 times 10 to the 15 atoms per centimeter cubed, right? So 100,000 times less atoms in the bulk than at the surface. So there's going to be a concentration gradient for sure. They're going to travel towards in the material, right? It says conditions are 30 minutes at 1223 K with D given, right? They give us the diffusion coefficient, and they give it in micrometers squared per hour instead of meters squared per second. That's fine. We can work with that. It says calculate the concentration at the diffusion length. So they want to know the concentration at the diffusion length. Well, we know that the diffusion length, that's a ballpark value. Diffusion length is equal to x root dt, right? And we also know that Cx minus C naught divided by Cs minus C naught equals 1 minus the error function of x over 2 root dt. Okay? So they told us that they want to know the concentration at the diffusion length, so we're solving for Cx. They tell us the diffusion length. That means that we can plug in root dt for x. That means that we don't actually need to even know d because it's going to cancel out, right? This right-hand side of the equation becomes 1 minus the error function of just 1/2, right? That's easy. In fact, because it's 1/2, that's 0.5, that was a value in our table. We know what the error function is. That's 0.5205. So this made it easy. We didn't have to do the interpolation that I showed you just barely. This is just going to be equal to 1 minus 0.5205, okay? On the left-hand side of the equation, we've got Cx, which we're solving for, minus the initial amount, which was 5 times 10 to the 15. That was atoms per centimeter cubed. Then down below it, we had the surface concentration, which was 4.5 times 10 to the 20. That's per centimeter cubed, minus the initial value deep within the material, 5 times 10 to the 15. per centimeters cubed. So the only thing we don't know in this expression is Cx. We can go ahead and solve for it. And when I do that, I find that Cx is equal to, let me find it here. When I solve for Cx, I find that it's equal to 2.15 times 10 to the 20th atoms per centimeter cubed. Okay? So this is a pretty straightforward question. This was a little bit easier than some because we didn't have to deal with the error function stuff. But there's a great problem on YouTube where we do work through using the actual value of the error function where you have to do the linear interpolation and all that jazz. Okay? All right. The last thing I want to cover today before we're done with Chapter 6 is talking about short-circuit diffusion paths. In the classroom, we talked about this before. We said if you're an atom and you want to diffuse from, say, the front of the classroom to the back of the classroom, you've got options. You could hop through the lattice, meaning you're kind of climbing over students, hopping from empty seat to empty seat, or hopping between empty seats in the little mini aisles between students. That's tricky. Or you could choose to walk down the rows between the students, right? The student sections are sort of crystalline. The regions between them represents a grain boundary. And so that region in between them is more open. And it's much, much easier to walk down the aisle than to climb over students. Therefore, the speed at which atoms diffuse is going to be way faster along something like a grain boundary than through the bulk. We call these short-circuit diffusion paths, right? They short-circuit. They're basically so much faster than the bulk that they're essentially a short circuit, right? So bulk versus those, you can see sort of the comparison, right? So here we're plotting the diffusivity, right, the diffusion coefficient, as a function of inverse temperature, again, 1 over T. By the way, this is the first time you're seeing this. It's a little bit odd that they do it. It's a bit obnoxious. What they're really saying is you take 1 divided by your temperature, multiply that times 1,000, and that equals the number that you're seeing right there, okay? So it's a little bit goofy. What this really means is if that's 1, then that means that your temperature must be 1,000 divided by your temperature equals 1. That just means that your temperature is also 1,000. If they're nice, they'll also include a scale up on the top, which is not linear, right? But they show you what the actual values represent. They won't always do that. So if you see a plot like this and you're wondering what on earth is happening there, you can interpret it pretty easy. Like if it's 1.5, well, what does that 1.5 mean? That means 1.5 times 1,000, so 1,500, right? Divided by your temperature. Let's see. I'm sorry, I messed that up. 1,000 divided by your temperature equals 1.5. So you could solve for your temperature that way, okay? And it'll be somewhere between 500 and 1,000, okay? So if that's the first time you're seeing those, that's what they're doing there. It's a bit odd, and they'll do it different ways, but it's generally like that, okay? In any case, your diffusivity, it goes from low temperature to high temperature. Grain boundaries, low temperature to high temperature. Surface, low temperature to high temperature. And these are just massively faster. If you find something roughly the same temperature, look at that. It is, by my count, so that is 1, 2, 3, 4, 5 orders of magnitude faster. So it's 100,000 times faster to diffuse along the grain boundaries than through the bulk, right? Over here, from the grain boundary to the surface, I'm counting 1, 2, 3. So 3 orders of magnitude, that's 1,000 times faster along the surface than along the grain boundary. So these are your short circuit pathways. That's what we're talking about when we describe those things. There's other ones, right? I think I've got some here listed. Things like dislocation cores. Oh yeah, right here. Dislocation cores. If you remember from chapter 8, a dislocation core. Let's jump back here real quick. If we jump all the way back to a dislocation. Yeah, right along here. See, in this dislocation, you've got the compression region and your tension region. There's this open space right there. If you're a carbon atom traveling through, say, an iron lattice, that is just a great spot to be. You're going to travel really quickly down that dislocation core because it's already sort of opened up a little bit. Okay? Okay, what else can we say about that? Generally speaking, what are the trends that we can say about diffusion rates? You will get faster diffusion if you have a more open structure, obviously. So, like the structures on my wall up behind me, some of those are much more open than others. There's just bigger empty spots between the lattices, and some of them are really close packed like metals. The more open the structure, the better your diffusion. Materials that have a lower melting point tend to be faster. If you've got secondary bonding, like polymers, instead of strong covalent bonding, that tends to be faster. Again, imagine a bowl of spaghetti, your polymers. Some of those are going to be bonded together, your polymer strands, but those are weak bonding forces, so pushing them apart so you can squeeze through with atoms or molecules is going to be faster. This is why polymers actually have a problem or a feature, depending on how you're thinking about it. Things can travel, they can diffuse through them pretty easily. So water, for example, can diffuse through lots of polymers, and that can be a good or a bad thing, depending on the application. Smaller atoms, faster diffusion. Cations, obviously, because they tend to be smaller because they've lost electrons, so they're really small. And then lower density materials, which is really just saying open crystal structure materials. Okay, so the opposite is true for the opposite characteristics. You will get slow diffusion for close packed structures, high melting points, covalent bonded, large atoms, anions, and high density materials. That will be your slow diffusion. Okay, if you're diffusing ionic species, then if these have a charge on them, then you can't just diffuse one type. Otherwise, you will build up a charge imbalance, right? So if this is your material, and you're, say, diffusing, say, oxygen 2-, right? If it's traveling to the other side and nothing else is happening, then you will build up a really big delta negative here and a delta positive over here. And eventually that electric field will resist future motion, right? Because now you have an ion traveling in the wrong direction to the electric field, and that's going to stop it. So it's going to reach equilibrium, and it just won't keep diffusing. So if you want it to keep on diffusing, then you need multiple species. Maybe you have hydrogen as well traveling, right? So if you have a minus species, an anion, and a cation both traveling, so you have coupled transport, then it can keep on diffusing, right? But that's what that's talking about, is coupled transport. We've already talked a little about polymers. Polymers, because they're weakly bonded and because you've got such big amorphous regions in those polymers where there's big open spaces, you can diffuse more than just individual atoms like carbon and nitrogen and hydrogen. You can actually diffuse whole molecules like water, methane, right? These things can leak really big molecules even. They're also susceptible to swelling and stretching, which can cause degradation of properties. In fact, if you do swell a polymer and then you measure its diffusion, it's going to be much higher in a swollen one. So when they make polymer ion fuel cells, which they're using for some vehicles, right, PEMFCs, polymer fuel cells, they intentionally soak the material that's going to diffuse hydrogen through it so that the hydrogen can travel faster in this swollen state because it spreads those atoms out a little bit. Okay. And then maybe the last thing I'll plot here is just a general plot to have in mind when it comes to diffusion in gases and liquids, which looks like this. First off, there's a big temperature difference, right? So if we plot it, let's draw our axes. So this might be something like the log of our diffusion coefficient, and something like centimeters squared per second if we were to put values on it. And then on the x-axis, you've got the temperature of the melting point divided by the temperature where you're at, right? So if you go all the way up to here, where you're at the temperature of your melting point, typically diffusion looks something like this, right? Right here, maybe that's your glassy transition temperature. So this would be maybe Tg, okay? That's going to have something like 10 to the negative 16. But as you heat it up to where now it's a liquid and it's flowing, this could be as high as 10 to the minus 4. So 12 orders of magnitude, just massive, right? And this value, that's really, really fast. So ions diffuse through a liquid, molecules, atoms, everything diffuses in liquid much, 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 much faster than a solid, obviously. Okay, that's diffusion. Next chapter will be on thermal properties.